everything you need to know about geosynchronous slash geostationary orbits. Let's do it. Okay, so here's your basic idea, and we're going to model this. This is the most fun part. We're going to build a model of this in Python, in 3D. Going to be awesome. So let's say I have some spacecraft in a circular orbit at this position right here. Well, there's only one force acting on it, and it's the gravitational force Fg. The magnitude of this gravitational force depends on the mass of the Earth, the mass of the object, and this radius, this r. So the further you go away, the lower the force. Now, if I think of just that one force, I know the acceleration has to be in the same direction. So I can write this, the F net magnitude equals ma magnitude, right? I'm just trying to do that because I don't want to be that guy that like disrespects vectors. I don't disrespect vectors. So up here I have the gravitational force, the magnitudes g, mass of the Earth, mass of the object over r squared, and this is equal to the mass of the object. And then the acceleration, if it's moving in a circle, then the acceleration is centripetal acceleration because it's changing the velocity vector. And so the magnitude of that would be v squared over r, or I could write that as omega squared r. So let's write that as omega squared r. So this is true in general, right? This is the angular velocity of the spacecraft. You'll notice here that the mass cancels. In the case where the mass of the Earth is super great, we can do this. If this has super mass, then actually everything changes because both things move. But I digress. So then I can divide both sides by r, and I get omega squared equals g, mass of the Earth, over r cubed, and I can take the square root. Omega equals the square root of g me over r cubed. That's the angular velocity to make a circular orbit. Circular orbit. So what would happen if I increase my orbital distance? I want to go up here. Well, if I increase r, omega gets smaller. If I'm at the if I'm at the orbital altitude of the space station, then the angular velocity is very high. It just takes like 90 minutes to make one complete orbit. So as I move further and further away, it takes longer and longer to move one orbit. At some point, we could get the orbital angular velocity to be equal to the rotational angular velocity of the Earth. And in that case, we have a geosynchronous orbit, because if omega orbit is equal to omega Earth, then it is a geosynchronous. If, and we're going to model this, if the orbital axis is the same as the Earth's rotation axis, meaning that the spacecraft is above the equator, then it'd be a geostationary orbit, and it'd actually look like it's in the same point in the sky at all times. Okay. In the geosynchronous, if they're not lined up orbits, this could be spinning this way, and the spacecraft could be going around this way. Every day, it'd come back to the same spot, but they're not stationary. It's not geostationary. Okay, let's model this in Python, and we can play around with all the different features. I want to make a rotating Earth, and I want to make a satellite that rotates around that Earth, and it's going to be cool. So, here are the parameters that I'm going to need. The mass of the Earth, I need that because it's in the gravitational force. The radius of the Earth, that's just to display it correctly. The gravitational constant g, 6.67 times 10 to the -11th. And this is the angular velocity of the rotation of the Earth in order for it to rotate one time per day. And I can't remember if I did a sidereal day, which is a little bit shorter, or a solar day. Technically, we should be using the sidereal day, but it doesn't matter in this case because we're not doing real gravitational work. But let's jump over to Python and start with building an Earth, and then we're going to see what happens. Okay, so here we are in Python. This is GlowScript Vpython if you haven't seen it before. And I'm going to go ahead and save this as a geostationary orbits. Save. Now I'm going to just go ahead and enter all my values up here before I forget. I'm going to move my paper so I can see it. Okay, so let's put G. Oops. It didn't save. That's fine. G equals 6.67 times 10 to the negative 11. I didn't explain how to do a numerical calculation. I apologize for that. I'll explain it as I go along. I do have other videos that explain that, so hopefully you'll forgive me. And I hope this is big enough. Let's just make it a little bit bigger. Okay, now let's do mass of the Earth. ME is 5.972 times 10 to the 24th. RE, I'll call it RE, is equal to 6.378 times 10 to the 6th. No units here because we're going to do a numerical calculation. If I put a letter there, then it just blows up. And then let's do omega. I'll just call it W. Omega is 7.3 times 10 to the negative 5th radians per second. Okay, so let's start with the Earth. So I'm going to say Earth equals sphere. I just want to run this in case you haven't seen this, see what it looks like. In GlowScript Vpython, we can build these three-dimensional objects. Sphere is one of them, and you can see that I actually can rotate this around in this 3D environment. I can zoom in and zoom out, so it's a real 3D environment. I can do more than that. Let's just go ahead and say position equals, I'm going to leave it like this, equals vector 0, 0, 0, so it's at the origin. The radius is going to be RE, and if I run that, everything looks the same. Because Python, even though I just made a ginormous sphere, Python zooms out so that it can see everything. Now let's do the real magic. Material equals materials dot earth. I think that's right. Oh no, it's not right. Material equals, let's see, what was it? Texture. It's texture. Texture, not materials. Texture, spell it right, equals textures dot earth. Check it out. Bam! Look at that. Okay, so there's your Earth. This is, you can rotate around and see it. This is a built-in texture map for your sphere. You can put this on anything, and it kind of maps the position of the Earth on there. And I'll go ahead and say that the lighting of this is not correct. The lighting sources, there's a default lighting source for Vpython that makes it a certain way. You can turn down the shininess of it and things like that. And that's emissivity equals 0. I can't remember. We can play around with what it actually looks like. It's an Earth. It's good enough for me. Now, I'm going to make the Earth rotate. That's the next thing I want to do. And I want to view it. I want to be able to see the orbits. And so I want the orbit to be in the XY plane, which is the plane that we're seeing right here, so you can see, instead of, so it doesn't go in and out of the paper, out of the screen. So I'm going to take that Earth and rotate it. So there is a way to do that in GlowScript Vpython. So if I do this, let's see. Let's go over here. I can say Earth.rotate. Rotate is a built-in function for different parameters. I just need to say what angle do I want to rotate it, what axis do I want to rotate it, and what origin do I want to rotate it about. So I want to rotate it 90 degrees. So I'm going to say angle equals pi over 2. I want to rotate it about the x-axis, right? So this is the x-axis, or that way. I don't know if my camera backs up or not. So I want to rotate the Earth like that. So I'm going to rotate it about the axis of vector 1, 0, 0. And then I also need to say what origin do I want to rotate about. If I don't say anything, I think it uses the origin. So I can say, or I think it's origin. Is that right? Yeah, origin. Let's say, let's do this the right way. Equals earth.pos. So that says it's rotating about the origin of the Earth. Let's see if that works. Didn't work. Oh, I said Earth. I said it's Earth. So there did it. It rotated the Earth like that. So now we're looking at it from the North Pole. Which way does the Earth? I can't remember which way the Earth rotates. I don't really care. Okay. So now what I want to do is to actually rotate the Earth. So let's just set up a time t equals 0. A time step. I'm going to say a time step of 100 seconds. And let's say while t is less than 2 days. So 2 days would be 2 times 24 times 3600. That's 2 days in. I guess I could do it here. Day equals 24. That's a solar day times 3600. So 2 days. So I can just say 2 times day. And now the next thing I'm going to do is I need a rate statement. Let's just do rate of 100. This will do 100 calculations every second. I think that might be too slow. Let's do 1,000. We can always make it lower. And all I want to do is to rotate the Earth. So how am I going to rotate the Earth? I'm just going to say Earth.rotate, just like I did before. Actually, I'm going to copy this whole thing. But I don't want to rotate it by an angle pi over 2. I want to rotate it about an angle omega d theta, right? I mean omega dt. So I'm going to say omega times dt, because if you say omega is delta theta over delta t, then delta theta would be omega delta t. So that is the amount it's going to rotate each little second. Now, what axis do I want to rotate about? The z-axis is the one that comes out of the board. So I want out of the screen. So I want to rotate about that. So it's going to be 0, 1, 0, and then the origin is the same. And no, that's the y-axis. The z-axis is right here. I wasn't thinking. Okay, I think that's good. And then I need to update time. T equals t plus dt. And now let's run it. Yeah, check that out. Was that 2 days? It seems like more than 2 days. Did it make 2 rotations? Let's see, let's change this to 500. Let's see, so there goes 1 rotation. 2 rotation. Okay, I did. There you go. It's rotating a little fast. Let's change that down to 100. And then I'm happy. Now you'll notice the first thing, the Python zooms out so you can see the whole thing. So now I have a rotating Earth. Next thing I want to do is to add a spacecraft. So let's just call it craft. Craft is going to be equal to another sphere, and let's say RC is going to be equal to, let's start it off at 1.1 times the radius of the Earth. And I'm going to start it on the x-axis, so the position is going to be equal to vector RC 0, 0. The radius, okay, so I'm going to have to make it really big so that we can see it. So let's say the radius is equal to RE divided by 20. I think that might work. And then let's say the color is color.yellow. And then let's say make trail equals true, so leave a trail behind. I do need the mass. Craft.m equals, let's say it's 1,000 kilograms, but it doesn't matter. Now, there's a couple of ways we could do this. I could calculate, let me switch back over to the paper because I should have done this before. Okay, so I have my spacecraft right here. There's the Earth, and there's the spacecraft. Let's say this is the momentum. The momentum principle says Fnet equals the change in momentum over the change in time for some small time interval. So I can say that's equal to P2 minus P1 over delta t. And then I can solve for P2. I get P2 equals P1 plus Fnet delta t. So P is going to be just m times v. And the force is going to be the gravitational force. Now, I did have the real definition of the gravitational force. Let me put it up here again. Fg equals negative g, mass of the Earth, mass of the craft, over r squared r hat. So if I have the spacecraft over here, and that's the vector r, then r hat is, negative r hat is going to be a unit vector pointing in the opposite direction. You need that, right? Because I want the force as a vector. If I just leave that off, I'd only get the magnitude, and I can't really model this whole thing. I can't find the new momentum. I have to have it as a vector. So, but that's the first thing I'm going to do. And I'm going to assume that if my time interval is short, 100 seconds is a fairly short time interval, then the net force is, the gravitational force is constant, and this works. Now I can use the definition of average velocity. V average is delta R over delta T, where R is a position. And so this is going to be R2 minus R1 over delta T. I can solve for R2. R2 equals R1 plus V average delta T. And I'm actually going to do this. R2 equals R1 plus P2 over M delta T. So I just updated the momentum. Instead of using the average velocity and the average momentum, I'm going to use the final momentum. And that works out okay. And then I can update time. So now I can go back up here and do the whole thing again. Because now that the position's moved, I have a new gravitational force. Even if it's just in a different direction, that does indeed matter. Okay. Now, one of the other things that we need to do is to find the initial velocity. So if I have this as my R value, I need to find the velocity. So just like I did before, I had the gravitational force. I'm just using a scalar here. Mass of the Earth, m over r squared equals v squared over r. Right? Because I don't want the angular velocity, I want the actual velocity. So that cancels m. That cancels. That cancels. V equals the square root of g me over r, where r is the orbital radius. So when I start off, I'm going to make that in the, since I have this in the x direction, the initial velocity is going to be in the y direction. Okay, I know that was quick. Crash course in numerical calculations, but now we can get started. So that means that I need to first calculate VC. VC is going to be equal to the square root of g times the mass of the Earth divided by RC. Now I can say craft.p. So one of those things in Python, we can do this object-oriented programming where we associate properties with the object. So I can say craft.p is the momentum of the craft. Okay, instead of having another variable. You could do it the other way too. So this is going to be craft.m times the vector, or let's say times vc, times the vector 0, 1, 0. So now it's going to be going that way in the positive y direction. Okay, I think that's good. So now, and I'm gonna, let's do this the way I want to do it. Okay, so the first thing I'm going to do is to calculate r. R is going to be I'm going to do this the correct way. It's going to be a vector from the center of the Earth to the spacecraft. So it's going to be craft.pos minus Earth.pos. That way, if my Earth is not at the origin, this will still work. Next, I can calculate the gravitational force. I'm just going to call it F. F equals negative g times me times craft.m times the unit vector r hat. And that's built into Python. I can just say norm r. That is r hat. And then I can divide by the magnitude of r squared. Again, magnitude is built into Python. So I can say mag r quantity squared. There's my F. Now I need to update the momentum. Craft.p equals craft.p plus F times dt. Now I need to update the position. Craft.pos equals craft.pos plus craft.p times dt divided by craft.m. I think that's good. Let's run it and see what happens. Check it out. Okay, that's not a geostationary orbit. And you can rotate this around and see what it looks like that way too. Okay, so now let's just go ahead and do a geostationary orbit. We already calculated what the radius of a. I did not calculate that. I calculated the angular velocity. I said if it was equal to the Earth. Okay, so let's go back over to the paper real quick. It's a good thing I can switch back and forth. So I said omega Earth equals the square root of g mass of the Earth over r cubed. And that gives me if that's true, I want to actually solve for r. I want to find out the value of r. So I'm going to square both sides, and I get g mass of the Earth over r cubed equals omega Earth squared. So r cubed is going to be g mass of the Earth over omega Earth squared. And then I can take the cube root of both sides. And that will be my radius for geostationary orbits. So let's do that. So I'm going to calculate that up here. So I'm going to say, oh, I didn't switch back. Sorry. Okay, so I didn't do anything. I promise nothing changed. So let's say RC equals parentheses G times mass of the Earth divided by omega squared. And then I need to raise that to the 1/3 power. I know that looks weird, but I think that's the only way to do it. Okay, then I recalculate that I calculate the velocity based on that. Let's move this up here. Oops, not that. Let's move this up here. Is that better? Maybe not. Okay. That's fine. So now I'm going to run it. There you go. Now you'll notice that this is directly over the same part of the Earth every second that it moves, every motion that it moves. And this is a geostationary orbit. Okay, so let's make a geosynchronous orbit just for fun. Okay, so in order to do that, I'm going to take the, I'm going to just give the, I'll make the planet orbit starting in the z direction. I can do that by going up here to craft.p and just changing this to, no, in the y direction. See, so I want it to go, if I go in the y direction, I did in the y direction. If I go in the x, and it had to be in the z. Okay, and let's speed it up a little bit. Okay, so there you can see that it's not in the same, the Earth is orbiting this way, but the spacecraft's orbiting the other way. So it's a geosynchronous orbit, not a geostationary orbit. But the geostationary orbits have to be above the equator in order for it to appear in the same part in the sky all the time. That's why if you go around and look at satellite TV dishes, they're always pointing somewhere south. But there you go. So if you want some homework, you can fix the lighting on this and make it more realistic lighting. That'd be fun. But I'll include this code down below, a link to this code down below, so you can play with it, and you should play with it, and I hope you have a good time.